Hello. We will now talk about chapter 2, section 1. Chapter 2 deals with a couple different kinds of distributions and really specifically where values are within those distributions. So we had a couple different measures of what we call placement, and that we're going to talk about in chapter 2, section 1. And then we've got a couple some properties that occur, and then we've got a special kind of graph called a relative cumulative frequency graph. And so that's going to be chapter 2, section 1. But the first thing is the concept of percentile and a z-score. So let's look at this problem right here. It says the number of computer sales that a worker at a computer company over 9 weeks is shown below. Find and interpret in context the percentile of 14. The percentile is the percent of values in the distribution that are at or less than our value. So the first thing, and numbers need to be in order, and they are, we're just going to count the number of them to find the percentile, count the number that are at or less than 14. So it's going to be 1, 2, 3, 4, 5, 6. There are 6 values at or left to 14, and there's a total of 9 values, so 6 ninths. Of course, that would be 0.6 repeating, which is 66.6 repeating percent. So it would be that percentile. Okay, so that's all there is to find in a percentile. It's just the percent of values that are at or below your value. By the way, and in some books, it may say the percent of values that are below a value. So sometimes you can see it differently, but this is the way that AP Stats has agreed upon in the last couple of years that we are going to do it. That's how you find a percentile. And so to interpret it just means to say this would be to say 14 is greater than or equal to 66.6 repeating percent of the number of computer sales in this sample. So that's what a percentile is, and that's what it means to interpret a percentile. The next thing is a z-score. Now, the z-score is just this formula. It is x minus mu over sigma. It is x minus the mean over sigma. Sometimes you'll see this written out with sample notation, which would be x minus x bar over s. It's sort of the same thing. It's still x minus the mean over the standard deviation. The z-score is the number of standard deviations that our value is from the mean. Okay, so let's find the mean and standard deviation of these values. And so you remember how to do that using your calculator. So what we do to get to the summary stats, remember, just like last chapter, stat and edit. And I put all of the values in list 1 right there. There's all the values. Okay, good. And so then we would do stat and calculate in one variable stats of list 1 and calculate. And so there's the mean 12.1 repeating. There's the standard deviation we use. We always use S, 6.470016. Okay, so to find, and so our mean, our X bar or our mu is equal to 12.1 repeating, and our standard deviation is going to be 6.470016. So to find the z-score, we use this formula. That formula is not on your formula sheet. You got to memorize it. So it's a relatively simple thing. You just say z is equal to our value, the x value, it's just a given value, 18, minus 12.1 repeating over 6.470016. And so let's see what that is. So we shall say 18 minus 12.111111 is equal to, and then divided by 6.470016. And so we would get 0.91018. 91, use at least 3 or 4 significant digits. And so there we go. And so what that means intuitively, is that this number is a little less than 1 standard deviation below the mean. And so that's what the next question is. That means, so intuitively, what is the z-score? It is the number of standard deviations the given value is from the mean. And it can be negative. I mean, if it's below the mean, then it's negative. So that's what a negative z-score would mean. It would be that the given value is below the mean. But that's all there is to doing that. It's a simple little arithmetic thing. You just got to subtract and divide there. And so that's the z-scores, the number of standard deviation values. Our value is from the mean. It's otherwise known as a standardized value. It's the number of standard deviations. So it shows us where our value is relatively. All right, and so that leads to the next problem. So Lucy gets a 93 in a test. Her z-score relative to the other scores was 2.1. So in other words, she was 2.1 standard deviations above the mean, which is pretty far above the mean. All right, so if the mean of the scores is 83, what's the standard deviation? Well, we'll use this formula. There's several problems dealing with, so x minus mu over sigma. So a very popular thing, there's the formula. They'll give you 3 of these values and you got to solve for the other one. So in this case, they gave us z, so z is 2.1. And then her value, x, that's our given value, that's 93, minus, and it says the mean, which is mu, or 83, over the standard deviation, which is sigma, okay, which we could use sigma or s, like I said before. And so we will do this. And so we say 2.1 is equal to 93 minus 83 is 10 over sigma, okay? Then I'll just use my algebra skills to solve for sigma. I got to get it out of the denominator, multiply both sides by sigma times sigma, like that. And so we'd have sigma times 2.1 is equal to 10, and then divide by 2.1, divide by 2.1. And so that, as it turns out, is equal to 4.7619. And so that's how you do that one. Okay, then we have this. This is sort of a popular little problem. All right, so Marty got a 79 on a test that had a mean of 72 and a standard deviation of 5. Sally got an 84 on a test that had a mean of 80 and standard deviation of 7. Who had the better score relatively? Okay, so certainly Sally got a higher score. She got 84, Marty got a 79. But how good is their score relative to the other scores? And so the way you can compare things relatively is by finding their z-scores, finding the number of standard deviations their value is from the mean. So the z-score for Marty, I'll put z sub m for Marty. And so his x value is 79 minus the mean of 72 over the standard deviation of 5. And so that would be 7/5, and that is equal to 1.4. So that is saying Marty's score was 7.4 standard deviations above the mean. You know, pretty far above average, all right? And so then the z-score for Sally, so her score was 84 minus the mean was 80, standard deviation of 7, so that's 4/7. And so her z-score was 0.5714, but above average, but Marty's was better relatively. So Marty had the better relative score, the better standardized score, the better relative score, because his z-score was higher, 1.4 to 0.5714. Boom. So there you go. All right, so that's how you do that. So that's working with z-scores and finding percentiles. Now, transformations. So transformations, what can happen to a data set is sometimes we can change units. We can change units from like seconds to minutes, or from like yards to feet, or whatever. So transformations are involved there. Or sometimes a distribution or list of numbers can get multiplied by something or divided, or maybe something will be added or subtracted. And you need to understand what happens to the summary stats. You know, the summary stats that we work with, we have, the mean, we have the mean and the median that are measures of center, right? And then we've got the measures of spread. We have the IQR, the range, and the standard deviation. So those are the main ones we are concerned about. What happens to them when you multiply, divide, add, or subtract? Okay, the thing is, when you multiply or divide, it affects everything, okay? When you multiply or divide a data set, all the summary stats, all the summary stats, measures of center and spread or of placement, like percentiles, all summary stats are multiplied or divided, depending on what you did. In other words, if you multiplied a data set by 2, you would in effect be multiplying all of the summary stats by 2. The mean, the median, the mode, the standard deviation, the IQR, the range, and any percentile or other measure of placement would also get multiplied. But when you add or subtract a value, the adding or subtracting does not affect measures of spread, okay? So how does adding or subtracting? It does not affect measures of spread, In other words, the standard deviation, the interquartile range, and the range. Okay, it does not affect, okay? But when you add or subtract, it does affect measures of center and of placement, measures of center, in other words, the mean and the median, and placement. Placement means like a percentile or a quartile in a placement. Let me show you what I mean by that. So this is kind of the most maybe difficult one you could face. So this one says Monique measures the height in feet of her ferns, getting the summary stats below. So here's the summary stats of all of her ferns. They have an average height of 4.1 feet and for the mean, and there's the median and so forth, okay? She puts the ferns on a 3-foot high platform and measures how high the tops of the ferns are above the ground in inches. So she changes it to inches by 12. And as you know, there's 12 inches in a foot. So that's by changing it to inches, it's effectively multiplying it by 12. What would the new summary stats be? So effectively what she's doing, she's changing it to inches. So she is multiplying every value by 12 because she did have it in feet. Okay, but she put it on a 3-foot high platform. Okay, and she's now measuring that in inches. Well, 3 feet, 3 times 12 is 36. So the transformation that she's doing to her data is she's multiplying everything by 12 by converting it to inches. And then by putting it on this 3-foot high platform, she's adding 36 to it. So what's going to happen is this, according to this, everything's going to get multiplied by 12. All of these measures of summary stats will get multiplied by 12. But this plus 36 is not going to affect the measures of spread, but it will affect the others. So the mean is a measure of center. So what you would do, the new mean is going to be 12 times 4.1 plus 36, and that, according to my records, is 85.2. The standard deviation is a measure of spread. It is not affected by adding or subtracting. So that would be 12 times 1.3, and so that would be 15.6. Okay, the minimum, that's a placement measure, so that would be 12 times 1.8 plus 36, and so that, in fact, would be 57.6. And you do the same with Q1. Q1, multiply it by 12 and add 36, and I won't write all of it out. That ends up being 66. All right, the median, that is affected by everything. So you would say, 12 times 3.9 plus 36, and so that would be 82.8. Q3, that's a measure of placement. It's the 75th percentile. So you multiply that times 12 plus 36. And so that would be 104.1. Hopefully I didn't make any arithmetic errors here. The maximum also multiplied by 12 and add 36. That's 109.2. IQR, measure of spread. It is not affected by adding 36. You just multiply it by 12. 12 times 3.2. And so that would be 38.4. Range, measure of spread, not affected by adding 36. So you just multiply it by 12 times 12 times 4.3, 12 times 4.3. That, in fact, is 51.6. Let me quickly try to explain why that is, okay, why this fact is in regards to transformations. Okay, so let's say if we had a data set, and let's pretend that our data set is, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's say our data set 1, 2, 3, 4, 5. Let's say it's the numbers 1, 2, 3, 4, and 5. And so that's x. Okay. Let's say if I multiplied that by 2, and I said 2x. So I multiplied every one of those numbers by 2. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now this 1 becomes a 2. I multiply all these numbers by 2. So it ended up being 2, 4, 6, 8, 10. So notice how the center of this got doubled. It was at 3, now it's at 6. But notice how they're twice as spread out now. So the range went from 4 and now it's 8. So they're and the IQR would be twice as spread out. So everything, when you multiply, everything is all the summary stats are multiplied by 2. But what if you added 3 to all the x's? So to all these x values, you added 3. So this would become 4, 5, 6, 7, 8. So now this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So our x plus 3, this 1 becomes a 4, this 2 becomes a 5, and so forth, 6, 7, 8. So the measures of center have been pushed up, as is the measures of placement like Q1 and Q3. But the measures of spread did not change. The range is still 4. The IQR would be the same, and the standard deviation, they're still the same. The standard deviation, the average distance from the center is the same here and here, okay? So that's just a little demonstration of why when you multiply or divide, okay, it affects everything. When you add or subtract, it does not affect measures of spread. Okay, there we go. All right, and so then we have a graph. So then we have a graph that we're gonna do, and I'm gonna do this by hand. Now, this is what is known as a relative cumulative frequency plot. We used to call it an ogive. Sometimes you'll see it referred to as a cumulative relative frequency plot. Doing this by hand has never been on the exam. And so you say, why am I doing it now? Well, I think it's important to do it like once or twice, just so that you understand what's going on with it. So make sure you pay attention to what I say here, because there are some things that are basically in the exam every year that deal with a graph like this, and they're easy to do if you know what you're doing. But I think in order to understand them, you sort of need to do it once. All right, so we're going to graph we're going to have to graph a relative cumulative frequency plot. So the way we're going to do that is we need to look at the frequencies, okay, and then find the cumulative frequencies and the relative cumulative frequencies. So let's make a frequency table. And so to do that, we need classes, okay? So we're going to make a frequency table, just like when we made a histogram. And so the numbers are going from 4 to 37. Okay, so with a difference of 33, I want at least like, I want at least like 4 or 5 classes. But let's say, so if I said, so 33 divided by 5, so I'm just going to make classes of size 6. It kind of doesn't matter. So I just need, the numbers are varying from 4 to 37. So I'll just try classes of 6. You could do it differently, maybe make it 5 or 7 or whatever. So 4 plus 6 is 10. And so we go from 10 to 16. And I keep adding 6, 16 to 22, and then 22 to 28, and then 28 to 34. And we keep going till we capture all the data, and then 34 to 40. Those are the classes. And now frequencies. I'm just going to write down how many are in each class. So from 4 to 10. Now, once again, these are inclusive on the left side. So 10 goes in this class. This class includes 10 and every number up to, not including 16, and so forth. So 10 goes in this class, 16 goes in this class, 22 goes in this class. All right, so from 4 to 10, we have 1, 2, 3, 4, 5, not including the 10. So this is 5. There's 5 in that. And then between 10 and 16, we have 1, 2, 3, 4, 5, 6. So 6 in that class. From 16 to 22, 1, 2, we have 2. 22 to 28, we have, let's see, 1, 2. So there's 2 there. From 28 to 34, we just have 1. And then we've got 2 there. And so there's our frequency table. Now, let's find what is known as our cumulative frequency. Cumulative. And now this, cumulative frequency is an important concept in stats. And so you need to understand what cumulative frequency is. All cumulative frequency just means add up the frequencies as you go. So when you look at the cumulative frequency, it tells you the number of values that are at or before this value. So you would just add them up. So there are 5 values that occur at or before this class. And then you just add the next number. So you go 5 plus 6 is 11. And then you go 11 plus 2 is 13, and so forth. 13 plus 2 is 15. 15 plus 1 is 16. 16 plus 2 is 18. And so our total number of numbers, the sum of our frequencies, our n, as we say, our sample size, is going to be 18. All right. And so that is what we call a cumulative frequency. Okay. So each number is the number of values that occur at or below this class. Then we shall find the relative cumulative frequency. And so, like I said, sometimes you'll see this referred to as cumulative relative frequency, which is the same thing. All right, so what that means is the word relative means find the percent or the proportion that are there, the percent or the proportion. So relative cumulative frequency, relative means find the percent. So this is saying 5 are there. Well, what percent is that? Well, it'll be 5 of the 18. So you just divide by the total, 5 of the 18. And so that, in fact, is equal to, when you divide that, that's equal to 0.27 repeating. Okay, then 11 over 18. Okay, so 11 divided by 18, that's 0.61 repeating. Okay, and so this is in essence the proportion that occur at this class or before it. So this is saying about 61.1% occur at this class or before it. Well, what concept is that we talked about earlier in this video? It's percentile. So then we have 13 divided by 18, and so that is equal to 0.72 repeating. And then 15 divided by 18 is, I believe, 0.83 repeating. 16 divided by 18 is 0.8 repeating, and then you always end up with 1. Now we're going to graph these numbers, and that's what is known as a relative cumulative frequency plot, which hopefully I'll leave myself enough room here. So I'll put it here. All right. So this is what is known as, whenever you see the term relative cumulative frequency, it is in essence a percentile graph. It is a percentile graph, and it is used to estimate percentile. So it's always going to go up to 100%. And I'll just put it in proportion. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1. Okay. And so now what you're going to put on the x-axis is all of your classes. So you're going to put, okay, 4 to 10, and then 16, and 22, and 28, and 34, and 40. And then what you're going to graph is on your right sides, on your right parts, okay, you're going to graph that percent. You're going to graph this number. Okay, so your ordered pairs are this and this. So at 10, we're going to graph. We start out at 0 on 4. That's just saying there's no numbers that occur before 4. All right, and then at 10, there's going to be 0.27 repeating, which I'll just 0.27 repeating is like right there. So I'll just put a dot there. And then over with the 16, I'm going to graph 0.61 repeating. So that's going to be up there. And then with the 22, I go up to 0.72 repeating, and that's going to be something like there. And then at the 28, 0.83 repeating, and that's going to be like there. And then at the 34, that's going to be 0.89 repeating. And so that's going to be like right there. And at 40, it goes up to 1, maybe. But, it'd be good to have graph paper. And anytime this has been in the exam, they always put grids on it. But then you connect the dots, and that is what is known as relative cumulative frequency plot. It always has to be, it's monotonic increasing. It always has to be either increasing or flat. Of course, if it's flat, it means there would be no values in that class. That's how you do it. All right. But the important thing is the questions that I'm fixing to answer down here. Making this graph isn't on the exam. I just think you need to make it to understand kind of what's going on. What is important is you're able to use this to estimate percentiles. Use this to estimate percentiles. And by the way, make sure this is the number of points a basketball player scores. So always label your axes. So this is number of points. Number of points. Okay, there we go. All right. Estimate, find the IQR. Estimate the IQR. So the main thing you've got, there's two things you got to be able to do with this graph. Estimate percentiles. Number one, estimate percentiles. Okay, that will be on your test. And number two, which is what I'm fixing to do. And number two is know the significance. Know the significance of steep or flat, steep or flat parts of the graph. And we shall talk about that. But the percentiles, you remember, all right. So the IQR, that's equal to Q3 minus Q1, right? And that's the 75th percentile minus the 25th percentile. So let's estimate that. So the main purpose of this graph is estimating percentiles. Let's find the 75th percentile. Well, you go to 75th percentile up here, relative cumulative frequency, and then go over to the graph. So at the graph, it's like right there. Okay, and then from there, you go down to the bottom. So I'm going to say it's a little more than 22. That's like, when you look at that, I'm going to say it's about, 23. So the 75th percentile is 23. The 25th percentile, you go to 25th percentile here. Okay, you go over, and that's going to be about right there. And so that's going to be, about 10 once again. So that's like 13. So there you go. That's one of the big uses of this graph is estimating percentiles. All right, and then it's a what's and this this is a misprint, and I apologize for that. Darn it, I was using the wrong thing. This should say of 30 points. I'd made up another example that dealt with a context with apples, so my bad in regards to that. So this should say what is the percentile of 30 points. Now, so what we would do there is we would go to 30 points on the x-axis. Well, 30 points is about right there. So I'll go vertically up to the graph. So that is about right there. Okay. Then I'll go from that over to here. I'm going to say about the 85th percentile. So the 85th percentile. So that is another use of this graph. Okay, there we go. So that's the first thing, to be able to estimate percentiles. The second thing is this, the significance of wherever the graph is really steep and wherever the graph is flat, okay? Wherever the graph is steep, it means there's a lot of data there. Wherever the graph is flat, it means there's not much data there. That's important to know, okay? So state the intervals that contain the most data points. The most data points are wherever it's steepest between there and there, between 10 and 16. So between 10 and 16. So of course you could get that off the table, but it wants you to look at the graph. All right, and the least data points. The least data points is wherever it's flattest, and so that is between like 28 and 34. So the least data points is 28 and 34. And lastly, it asks us to draw a histogram. Now we could draw a histogram just using the frequencies, just like we did in chapter 1. But to look at this graph and estimate the histogram, we would say this. We would say wherever they're steep, there's a lot of data points. Wherever it's sort of flat, there's not much. And so let's estimate this. So I'll write down these numbers. And so I'll go, okay, so let's go 4 and 10 and leave myself a lot of room here. 4 and 10 and 16 and 22 and 28 and 34 and 40. Okay, it's really steep between 10 and 16. So that means there's a lot of data points there. So I'll put that going really high. All right, it's sort of flat in here. So that means there's not many data points in those classes. So I'll put that down here. Now, if you had a really good, graph paper graph, you could estimate that. And it's not really that steep there. It's sort of steep there, kind of in between the two. So that would be like that. So it's sort of steep. So there you go. So that would be the estimate of the histogram. And that's it. That's section 1. If you got any questions about that, please let me know. And I hope you just have a wonderful day.